All right, we've made it. Our very last video of Chem 121, and I'll try to make it brief because I could go on about the history behind this for quite a while. But let's talk about nuclear energy going back to 1903, right? So 1903 was a breakthrough year, and it was theorized that we could convert matter into energy. So it was theorized that all matter has energy inside of it. We knew that radioactive materials contained this energy, but this was different. This was saying all material has energy. So I'm going to put in here not just radioactive matter. All right, and then we went, a couple more decades until or actually not even a decade, to 1905, when this guy came along, Albert Einstein. And Einstein wasn't a chemist, he was a physicist, but he realized that there was physics and math behind this, and he came up with his famous equation E equals mc squared, where E is going to be our energy, m is going to be our mass for our matter, and c is going to be the speed of light. And the speed of light is 3.0 times 10 to the 8th meters per second in a vacuum. So using Albert Einstein's theory, you can see that a really, really small amount of mass multiplied by this enormous value of the speed of light squared would produce a tremendous amount of energy. So then the thought was, well, if we can convert even a tiny portion of this mass to energy, we could create enough energy to provide any human being on this planet with all of the electricity needs that he or she might need for the duration of their lives, right? However, you can imagine pretty quickly the military officials said, wait, we could also convert this energy into bombs. And you can see where I'm going with this. And that leads to this next step. Around 1939, there were chemists and physicists both in Germany and the United States that were working on trying to figure out how to create this energy. And the theory was confirmed almost on accident. So the theory was confirmed by bombarding an isotope trying to make a heavier isotope. So let's just write this down. So the theory was confirmed by bombarding uranium-235 with neutrons. And instead of making a new isotope, they actually just ripped it apart. So instead of making a new, heavier nuclei, it split apart. And released energy. One of the things that always blows my mind was that one of these experiments was done in the middle of Chicago, and they were doing it, in a pretty populated area without really understanding how much energy was being released. But luckily, they had a plan in place to control it. And as you can imagine, because they were using neutrons, they were able to basically stick moderators into the reaction and try to slow it down. But it produced a tremendous amount of energy in a relatively unsafe area, and it was kind of the cowboy days of radioactive nuclear chemistry. And if you think back to our last video, when we split this apart, this is called fission, right? Fusion is the opposite. It's when you fuse two things together, but this is fission. We're going to rip these things apart, right? And I wanted to show you just a really generic image of this. I'm not going to expect you to understand all of this because, to be perfectly honest, I don't. I'm an organic chemist. This is way beyond my area of expertise. But here's the idea here. We've got this uranium-235 atom, and we're going to put in this neutron, and we're going to slam it. When it happens, it really quickly does convert into a heavier isotope, uranium-236. But that isotope is so unstable, it splits apart into two new elements. It splits into barium and krypton. But the neatest thing from this is that it ejects out new electrons. So it ejects neutrons that can continue to hit other uranium-235 atoms. And this is called a chain reaction, right? So basically, you just need to initiate this first hit with that first neutron, but the new neutrons that kick out at the end keep this reaction going over and over and over again. All right, so let's take a look at the ramifications of this. So here's one of the images from our book. And I'm just going to show you the images and try to avoid writing too much because, like I said, I just want you to understand the broad idea of this. So up top, what we have is a critical reaction. And what this is it's a constant rate. And it's controllable. So for example, if we put moderators in, we could absorb some of those neutrons. Maybe instead of having 4, we cut it down to 3 by catching some of them. But the overall idea is that this is controllable. Down here, we've got a supercritical reaction. This is one that's an expanding branch. And what this does is it leads to an explosion. All right, so this is the whole idea behind the atom bomb, right? If you've got some sort of fissile material, something you can split apart that also ejects off neutrons, you can create a chain reaction that branches and occurs so quickly that the amount of energy that you release is explosive. Okay, and I wanted to show you, just from a history point of view, what goes on in an atom bomb. All right, when the first atom bombs were developed, they had 2 different technologies in place. We had the spherical configuration on top, and then we had what was called the gun or tubular configuration on bottom. So in the ones that are still used today, what they do is they have a core, and then they have subcritical masses kind of around the core placed symmetrically around. And then they put explosive charges on the outside so that when those explosive charges go off, they create what's called a supercritical mass. So when a supercritical mass is formed, this will lead to a supercritical reaction. Expanded branching. Whoops. Oop. Reaction. All right, and that's what leads to the nuclear explosion. So it's basically a compression of the nuclear material. The gun configuration was a little bit different. Instead, what they had was a subcritical mass on one side, meaning it wouldn't run away and form an explosive, and then a second subcritical mass, and they would blast them together, and this would create a nuclear explosion. So Fat Man and Little Boy, the bombs dropped into Japan, were actually 2 different types of atom bomb. Like I said, this top one is the standard one that is used today. It's just a lot easier to set up, requires less weight, and is cheaper to produce. So that's what they were studying during the Trinity project. Obviously, the bombs that we have today are also much bigger than those first bombs that were dropped in 1945. In fact, we have hydrogen bombs today. So I just briefly wanted to describe what a H-bomb is. But an H-bomb, in the most generic terms, is a fission-fusion bomb. All right, so the initial step is fission. So basically your traditional atom bomb. But that energy that results is used to fuse two lighter nuclei together and create a second fusion reaction that also releases a tremendous amount of energy. So if you look at the nuclear yields from, let's say, the initial bomb on Hiroshima versus the Castle Bravo tests that the US did in the 1950s, they are night and day different. The first atom bombs look like firecrackers compared to the H-bomb. So pretty scary stuff. The book goes into this in a bit more detail, but I thought we'd end on a lighter note because the whole goal with this was to provide cheap, green, carbon-free energy for any human being on the planet, right? So this leads to nuclear reactors. And the whole idea with the nuclear reactor is to have a critical nuclear reaction, but one that could be moderated and maintained over ideally decades, right? So what you have is you have a nuclear reaction taking place inside of a reactor core. And this gets obviously pretty hot. But the nice thing with this is you can move coolant around. And this coolant obviously will be quite warm, but then it goes into this heat exchangers, hands off its heat, and then cold coolant moves right back in. And so inside this area, it's going to be quite hot. You pump cold water in, becomes steam, goes through a turbine, and continues through. So it's essentially a closed loop type system that can then be used to turn an electric generator and provide a huge amount of energy. The main problem with these is a couple of things. Number one, I brought up the example of Chernobyl. During Chernobyl, they did a test that essentially caused their reactor to explode. When that exploded, obviously all the nuclear material was exposed to the environment, which was awful, right? And then you might have heard about Fukushima too. So what happened in Fukushima? Well, in Fukushima, the reactor, at least after the earthquake, was intact. But what happened was the power got shut down that stopped this pumping process. They even had backup generators, but unfortunately, the way they designed the reactor, the backup generators got hit by the tsunami wave, which meant that they didn't work well. So what happens if we close this loop and we shut this down, right? Well, then the reactor gets hotter and hotter and hotter, and it's believed that at least one of the reactors has melted down in there, and they're trying to figure out a way to keep it cool, to keep it from potentially exploding. So today what they're doing is pumping in tons of water, pumping it right back out into storage tanks because at that point it's now radioactive water, and they're trying to figure out a better long-term solution for what happened in Fukushima. So there are safety concerns. I did, as a chemist, want to assure you that there are technologies that are far safer than this design. This is just the classic design. If you are interested in reading more about it, there's actually a company in the Puget Sound region called TerraPower, and they are working on a technology that's really neat called a traveling wave reactor that is much, much, much safer than this, where we don't have to worry about pumping all this coolant to keep the reactor cool during a potential emergency. It'll actually shut itself down, which is pretty dang cool. All right, so that's it. Make sure that you spend a good amount of time studying for the final. The final will be cumulative, and I want to make sure that everybody understands the key concepts from each of the various chapters. So you may want to go back and take a look at your notes. All right, good luck studying, and let me know if you have any questions.